Hello, I've got two big dot points to try and cover today about special relativity. They're so big they're taking up my whole screen here. Um, these are really all the bits of evidence that prove that Einstein was right. So we said before, Einstein's thought experiment led him to the conclusion that at high speeds, distances and times are relative. They change depending on the observer. And here we have four great examples of this happening that we can measure, and we can measure them precisely enough to actually be sure that Einstein's correct. Einstein didn't just say that length and time were relative, he also used Lorenz's equations. That's these equations in the dot points here. This one for time, this one for length, and this one for mass or momentum. Use those equations in order to calculate what should happen in certain situations, and we have confirmed those. The first example here is the observations of cosmic origin muons at the Earth's surface. So muons are a type of particle. When we create them in our own particle accelerators, they have an average lifespan of about 2.2 microseconds before they decay. 2.2 microseconds is very, very short. Now, muons are also created when cosmic rays, particularly protons, strike the upper atmosphere, which is 10, 20, 30 kilometers above the surface of Earth. So let's get some things drawn here. We have the surface of Earth. We have a distance which is, at least 10 kilometers above the surface, 10 kilometers plus above the surface. Protons are striking the atmosphere and they're creating this fast-moving muon. Okay, now this fast-moving muon is so fast it can travel at about 98%, 99% the speed of light. At 98% the speed of light, with an average lifespan of 2.2 microseconds, they can travel a bit less than a kilometer, maybe 700 meters before they decay, and we shouldn't be able to measure them anymore. So yeah, really, they should only be traveling a distance of about 700 meters before they decay. So if we have detectors here on the ground, we shouldn't really be able to detect very many of them at all. If we compare a detector on the ground and another one high up on a mountain, the differences in the amount of muons that we measure should be really high. We should measure a lot up here in about the length that they should be able to travel, and we should measure almost none, practically zero muons striking the bottom. But what do we actually detect? We detect a lot of muons at the bottom. Why is that? So from our perspective, from our frame of reference, looking at the muons, because they are moving so fast, their time is dilated. Their time slows down. Essentially, they age slower. If they had a wristwatch, it would tick by slower. So we look at the muon, we look at their wristwatch ticking past every microsecond, and by the time it takes that to reach 2.2 microseconds, the muon has made it to the ground, because from our perspective, our time is running faster than the muon's time. Now, if you think about what the muon is experiencing, if you were traveling with the muon, if you were the muon traveling towards the Earth, your time would tick by at normal speed. You look at your watch, 2.2 microseconds, poof, and you're dead. So how can you travel further than 700 meters? Well, the answer is you don't. You actually just travel about 700 meters. Since you're moving towards the Earth at high speed, you see the Earth traveling close to the speed of light towards you. Right? So this distance here, this 10 kilometers, contracts until it's only about 700 meters, right? Because you, from your point of view, from your reference frame, the Earth is moving. That makes its length shrink so that it takes only 700 meters for you to travel. From the Earth's frame of reference, looking at you, you are moving at high speed, so your time is dilated, meaning that you get to travel for 2.2 microseconds of your time compared to our more time than 2.2 microseconds, I think like 4 or 5 microseconds or something. Okay, these are what these two equations here are saying. So time dilation for us observing the muon, or length contraction for the muon observing the Earth, both of which end up agreeing that the muon can reach the ground, and this is confirmed by experimental evidence. A little bit about these equations. The way they work is they all have this term, v squared divided by c squared, 1 minus v squared over c squared. So at a normal velocity, I can walk at 7 meters per second. V squared is practically 0, 7 times 7, divided by c squared. C is 300 million meters per second. So 300 million squared is a very large number. My velocity squared divided by that huge number is practically 0. So 1 minus all of that is practically 1. Square root of 1 is practically 1. The length that you observe me compared to the length that I observe myself when I'm walking is basically the same. Yeah. However, if my velocity approaches the speed of light, suddenly this whole term here is getting close to 1. 1 minus that number is now quite small. And so now you would be timesing the length I observe myself by quite a small number, so shrinking my length, and that would be the length you observe. So this, you can see how the terms in these equations, how they logically lend themselves to not being evident at normal speeds, but at close to the speed of light, they can have quite large effects. All right, that's the first one. What's our second one? Atomic cloths, the Hafele Keating experiment. This one is cool because it is so intuitive. It is what you would try to do if someone said to you, oh, the faster you move, the slower time goes. What do? You get the fastest moving object, like car you can get, in this case, like a plane. You put clocks in it, you fly those planes, and you see how fast their time goes. You compare them to someone staying on the ground with a clock. We need atomic clocks, really, really accurate clocks in order to measure this, because we're looking at nanoseconds here of difference. So Hafele and Keating, they had 4 clocks, 2 of which they flew, 2 of which stayed on the ground. The flying clocks flew east and west around the Earth. So let's draw this out. We have the Earth, we have one clock flying one way, one clock flying the other way. This one's flying east, this one's flying west. They're going the whole way around the Earth. So let's say the west one can be the red one, whole way around, back to where it started. The east one also goes all the way around, back to where it started. And then you compare all 4 clocks, the 2 that flew and the 2 that stayed on the ground. Now this is a combination of special relativity and general. The special relativity part, which is the particularly important part for this, is this one up here, time dilation, because the clocks in the planes are moving faster than the clocks on the ground. We would expect their time, we would expect to measure their time as less than our time. They will age slower, less time will pass. However, general relativity has a part to play here too. General relativity isn't mathematically covered in this course, but suffice to say that under large gravitational fields or under high acceleration, time goes slower. So down on the surface of Earth, we're under a stronger influence of Earth's gravity, time goes slower than if we go into upper atmosphere or if we go into space. Time will go faster for them because they are under less influence of gravity. The maths of this is famously very difficult to do. So what did they discover? Well, the one that was traveling east, because of the jet streams, happens to go quite fast, and so the effects of special relativity were bigger than the effects of general relativity. So special relativity is making time go slower, general relativity is making time go faster. So the slower one out, and it lost 59 nanoseconds in its trip around. The one going west was not going as fast, so general relativity won out and it gained 273 nanoseconds. Okay, it's gaining seconds, well, nanoseconds, because time's ticking by faster for it because it's further away from Earth's gravitational field. And this was within the margin of errors that they calculated that it should be. They calculated using the time dilation equation, but also the general relativity equations. That's atomic clocks. evidence from particle accelerators. So here we have to talk about another consequence of special relativity. Light is a massless particle, and as a massless particle, it cannot be accelerated. If you think about Newton's law, F equals ma, if you put a force onto a particle of light, onto a photon, which you can't, the amount of acceleration that it would experience is infinite as it has zero mass. So instead of accelerating, light particles are born traveling at the max speed possible of the universe. So what is the consequence of this? If I had a particle with mass traveling at or extremely close to the speed of light, and I give it energy, what happens? Can it gain kinetic energy and not go above the speed of light? Does the energy just disappear? The answer is it does gain kinetic energy, but it does it by increasing its inertia or increasing its mass instead of by increasing its velocity. So that's where this other equation here is coming from. This equation is talking about its momentum. So here we have mass times velocity. When you push a particle to give it extra velocity, you're also giving it extra mass. The closer you get to the speed of light, the more the proportion is towards giving it extra mass rather than extra velocity. This is stopping any physical object, any object with mass, stopping it from achieving the speed of light, because as you push it faster and faster, its mass gets greater and greater, or its inertia gets greater and greater, so you can't continue to push it effectively. This maintains conservation of energy because it's still gaining kinetic energy because its mass is increasing, but it does not violate the special theory of relativity, which is good. What's our experimental evidence? It comes from particle accelerators. These are objects that can accelerate protons to very close to the speed of light. As they do, we have very precise measurements of the amount of kinetic energy that those particles have. The energy continues to rise even though there are only small changes to their velocities, going from between, say, 99.3% the speed of light to 99.7% the speed of light is a huge increase in kinetic energy compared to just a small increase in velocity. And that's because of the extra momentum gained by those particles. The best particle accelerator we have now, of course, is the Large Hadron Collider under the ground in Europe. Okay, and this also covers the limitation on the maximum velocity of a particle, which is any particle with mass cannot travel at the speed of light. Any massless particle will always travel at the speed of light and never faster or slower. Unless it's traveling through another medium, in which case, yes, speeds change. Gets slower, never faster. Okay, last bit, evidence from cosmological studies. So my interpretation of this is the solar eclipse experiments that really confirmed Einstein's theory of general relativity. What happens is his theory changes the way we thought about space. It says that space is that space-time is curved by objects with gravity rather than just being a constant. And because it's curved, any light that's traveling through curved space is going to curve around itself. So he thought that from the Earth, if we looked at the sun as an object with a high amount of gravity will bend space-time, and light would be able to travel around the sun because of this bend in space-time. So we'd actually be able to see objects that are technically behind the sun, right? We'd be able to see them from Earth because their light bends around. Okay, if they traveled straight and went straight through the sun, they just hit the sun and we wouldn't be able to see them. So all we have to do is get a telescope, point it towards the sun, have a look at what stars we can see around the sun and see if their positions are not where they're meant to be, right? If we are looking at this red star here on Earth, we would be seeing it, as if it was in this position here because its light is bending around the sun, when really we know it's in this position here, because when the sun goes away, we can see it in the blue position, not in the red position. So the sun's bending its apparent position, just kind of like a glass of water can bend the light from a straw or something. So seems easy, right? Wrong. The light from the sun itself is too strong, it overpowers all our telescopes. We can't see stars directly next to it. The answer, we just need to put a giant shade in between us and the sun, just blocking the sun, allowing us to see those stars on the outside. This giant shade is called the moon. So we have to line it up exactly so that there is a solar eclipse, the moon is in front of the sun, dimming the light enough so that we can measure the positions of the stars around it. This happened, I think it was 1919. We did some measurements and confirmed Einstein's theory of general relativity. Now, it's not just that the position of the stars changed, and that showed that there was a curvature of light. According to Newton's laws, if we kind of do a half Newton's laws, half Einstein's idea of gravitational lensing, the position of the stars would still change slightly. The only difference is in the amount they change. So they actually did the calculations, worked out how much this angle of the actual position versus the observed position, what that should be under Newton's laws, what that should be under Einstein's laws before they measured it, and when they measured it, it agreed with Einstein, which was huge. He overthrew Newton, who had been the big guy in physics for centuries. Okay, 2 huge dot points, 1 more to go for this module.